This is a presentation of the RENOPS Scheduler component, explaining the functionalities and technical implementation of the component. We will start with describing the problem and challenges that lead the development. Then we will continue with introducing the RENOPS Scheduler, following with demonstration of RENOPS components and its data sources. Lastly, we will show a short demonstration of RENOPS in action. Let's dive in. First, we will describe the challenges of fluctuating electricity prices and environmental impacts, explaining why a new solution is needed. We live in a world where electricity powers almost every aspect of our lives, from the devices we use to how we heat, cool, and move through our day. But not all electricity is created equal, and more importantly, it's not priced equally either. Electricity prices can fluctuate drastically depending on the time of day, regional demand, or even how much renewable energy is being generated at that moment. They can vary throughout the day. At times it's more affordable and cleaner, while at other times it may be costlier and more carbon intensive. This variability in electricity cost and carbon footprint presents both a challenge and an opportunity. For organizations and individuals running energy-intensive workloads, there's a clear incentive to shift flexible tasks to times when electricity is cleaner and cheaper. However, manually tracking price and carbon signals and rescheduling jobs accordingly is complex and time-consuming. That's why we created a solution to automate this process and help users make smarter, greener, and more cost-effective decisions. This chapter introduces RENOPS, a Python tool that schedules energy-intensive tasks for maximum efficiency and sustainability using real-time environmental and economic data. RENOPS is a Python-based scheduling solution designed to optimize the execution of energy-intensive tasks such as data analytics, AI model training, or any script based on environmental and economic factors. It does this by shifting tasks in time to periods with the highest predicted renewable energy availability, lowest energy price, or lowest carbon emissions, or shifting tasks in space, GeoShifting, to the optimal geographical location among a set of endpoints based on the same metrics. It provides both a command line interface, CLI, and a Python API for integration into other workflows. The solution fetches real-time and forecasted data from external sources, e.g., for renewable potential, energy prices, and carbon emissions, and uses this data to make scheduling decisions. Scheduler is focused on optimizing when a command should be executed at a single specified location. The user provides the script to run, the location, the estimated runtime, and a deadline. Scheduler retrieves forecast data for the chosen metric at that location and analyzes it to find the optimal time window within the deadline and runtime constraints. It then waits until the identified optimal time and executes the script. This method is best suited for situations where the location is fixed, but the timing is flexible, allowing the user to schedule tasks for periods with the most advantageous conditions, such as lowest cost or highest renewable availability. GeoShift, in contrast, is designed to optimize where a command should be executed by evaluating multiple possible locations. It takes a list of endpoints, each with a location and a command, and for each one it fetches the current value of the selected optimization metric, such as energy price, emissions, or renewable potential. GeoShift compares these current values across all locations and immediately executes the command at the location that offers the best metric, according to the user's preference. This approach is ideal when you have flexibility in where a task can run and want to take advantage of the most favorable conditions at the present moment. The system offers different optimization options tailored to various types of shifting. One option is renewable potential, which schedules tasks at times or locations where the share of renewable energy, such as solar or wind, is highest. This helps maximize the use of green energy and reduces reliance on fossil fuels. Another option is price, which schedules tasks during periods or in places where electricity prices are lowest, allowing users to minimize operational costs by taking advantage of market fluctuations. The third option is carbon emissions, which schedules tasks when or where the carbon intensity of electricity generation is at its lowest, thereby helping to reduce the environmental impact by minimizing CO2 emissions. In this section, we will demonstrate how the RENOPS components work and provide a description of each component. The user starts the workflow by running the CLI or importing the package, choosing either Scheduler for time-based optimization at a single location, or GeoShift for location-based optimization across multiple endpoints. The main operator, scheduler or GeoShift, gathers user inputs and requests data from the data fetcher, which uses the geolocation layer to resolve locations and fetches relevant forecast or current data from the RENOPS API. Config and utils provide supporting settings and helper functions throughout the process. The main operator then selects the optimal time or location based on the chosen metric and executes the user's script or command accordingly. RENOPS API service acts as a central information provider through an easy-to-access API, collects and combines data about weather, electricity prices, and carbon emissions from trusted sources, makes this information available to other applications in a standardized format. The client sends a request to a RENOPS API endpoint. The API layer receives the request, parses the input, and calls functions in the prediction logic. The prediction logic may use helper functions from the utilities module to process data or perform fetching and pre-processing raw weather or energy data. The API layer then returns the prediction result to the client. Unit tests are used to directly test the prediction logic and utility functions. The demo notebook demonstrates usage by calling the API or directly using the prediction logic and saves the output. The workflow starts when the user defines their preferences, such as minimizing electricity costs, reducing carbon emissions, or maximizing renewable energy use. The RENOPS Scheduler then communicates with the RENOPS API, requesting forecast data for different locations and time periods. The API collects and returns detailed information, including hourly forecasts for renewable potential, prices, and emissions across various regions. The scheduler processes this data by filtering and analyzing it, not only to find the best time to run the user's task, but also to identify the most optimal location. This means the system can recommend shifting the task both in time, scheduling, and in space, GeoShift, to take advantage of the best possible conditions. As a result, the workflow enables users to make smarter decisions about when and where to use energy, ensuring each task is executed at the most favorable moment and place based on real-time data-driven insights from the RENOPS API. Here we present all the data sources used by RENOPS and their purposes. These sources deliver detailed weather forecasts, including solar irradiation, temperature, and cloud coverage. Data is fetched via OpenMeteor API, and it is processed to estimate the renewable potential, a measure of how much renewable energy, such as solar or wind, is likely to be available at a specific location and time. By maximizing renewable potential, users can align their energy use with periods of high green energy availability, reducing reliance on fossil fuels. ENTSO-E provides day-ahead electricity price data for European countries and regions. These prices are set through a daily market auction and published for each bidding zone, reflecting the expected supply and demand for each hour of the following day. By accessing this data, typically via the ENTSO-E Transparency Platform API, which returns hourly prices based on location and date, the scheduler can identify the cheapest hours to run energy-intensive tasks. This helps users lower their operational costs and take advantage of market price fluctuations. In practice, the system automatically maps your location to the appropriate bidding zone and retrieves the relevant day-ahead prices from ENTSO-E's API for use in scheduling and analysis. Carbon emissions dataset offer forecasts of the carbon intensity of electricity generation, typically measured in grams of CO2 equivalent per kilowatt-hour. By scheduling tasks during periods of low carbon intensity, users can minimize the environmental impact of their energy consumption. The carbon emission data is sourced from a machine learning model TFT developed by XLAB, which provides predictions specifically for Slovenia based on historical and forecasted grid data. This data is used to inform users about the expected carbon footprint of electricity usage, enabling more sustainable decision-making. Weather data is fetched from the OpenMeteor API and then parsed into a Pandas data frame. Relevant columns, such as solar irradiation and cloud coverage, are selected. Timestamps are converted to a standard format, and the data is organized into a user-friendly output structure. Day-ahead electricity prices are retrieved using the ENTSO-E Pandas client. This data is converted into a data frame, timestamps are standardized, and the results are formatted as lists or arrays for easy use in applications or APIs. Carbon intensity forecasts are obtained from the XForecast endpoint, which uses a machine learning model trained on Slovenian grid data. The predictions are post-processed to ensure correct formatting. Timestamps are standardized, and the output is structured as arrays or dictionaries for user consumption. We will cover how to set up the RENOPS Scheduler in your environment and demonstrate how to use its two main features, the scheduler and the GeoShifter. To get started with the RENOPS Scheduler in your local environment, first make sure you have Python installed and all required dependencies from the requirements file. The recommended way is to use Conda for environment management, which will set up a dedicated environment with all necessary packages. Next, you need to export your RENOPS API key as an environment variable. This key is required for the tool to access live forecast data from the RENOPS API. Once your environment is ready, you can create a Python script with blank content and start working with the scheduler. Alternatively, you can install the package directly from PyPI. After installation, prepare your Python script as before and make sure to export the RENOPS API key so the tool can function properly. This setup ensures that you are ready to use both the scheduling and geoshifting features provided by RENOPS Scheduler. First, define a task function such as weekly retrain, which simulates a distributed learning job by accepting parameters like the number of accelerators, their type, power, and unit, and then prints out the configuration and total power consumption. Next, initialize the scheduler by creating an object with parameters specifying the expected runtime, deadline, location for forecast data, the optimization metric, such as renewable potential, the task function to execute, and any required arguments or keyword arguments. If the location is not specified, then the scheduler will automatically detect your location. Finally, run the scheduler, which will automatically fetch the relevant forecast data, analyze it to determine the optimal time window within the deadline, wait until that time, and then execute the task function with the provided arguments. These results show that the scheduler has analyzed the forecast data for Berlin, Germany, and determined when renewable energy potential will be highest within the specified deadline. It displays the location, the deadline by which the task must be completed, and the optimal time window it has selected for execution. The renewable potential value at that time is shown, and the script indicates how long it will wait before starting the task to ensure it runs during the most favorable conditions. To use the GeoShift feature, first define a dictionary called locations, where each entry maps an endpoint name to its geographical location and the SSH command needed to run a script, such as test.py, on that remote machine. Next, create a GeoShift object by providing this locations dictionary and enabling verbose output for detailed information. In this example, we will set the optimized on type parameter to price, so the tool will select the location with the lowest electricity price. Finally, call the GeoShift method. This will fetch the current electricity price for each location, compare all locations to identify the one with the lowest value, and then execute the corresponding SSH command on the optimal endpoint, running the script remotely at the best location. These results show that the GeoShift tool has evaluated the current electricity price at each specified location. It displays the metric value for each endpoint and identifies Madrid, Spain, HPC2 as having the lowest price. The tool then selects this location as optimal and proceeds to run the specified command on the remote machine in Madrid. Now let's go through how to set up RENOPS Scheduler and GeoShifter. We'll start with the scheduler. First, we need to import the scheduler by importing the scheduler class. Then we'll create a simple train function, which represents a high-demand energy process and accepts a few arguments. After that, we define the scheduler attributes to match our needs. Let's set the runtime of the process to 5 hours, the deadline to 72 hours, and specify that it should run in Berlin, Germany. We'll optimize the scheduling based on the renewable potential score and define the actual process to run along with the values passed into it. Once everything is configured, we're ready to execute. The scheduler calculates that the best time to run the process for the defined duration within the next 72 hours in Berlin is in about 50 hours. Now let's move on to GeoShifter. First, we need to import it by importing the GeoShift class. We then define a set of locations, and for each location, a script or command that should run if that location is selected. In our case, we'll change the configuration to use our capital, Ljubljana. We'll use a simple script called test.py, which prints the name of the location chosen by GeoShifter. Next, we initialize the shifter with the predefined locations and set the optimization type to price. Finally, we run it using the shift method and wait for the result. GeoShifter determines that the best place to run the task at the moment is Madrid, Spain, because the price there is less than half of that in the other two locations. In conclusion, RENOPS Scheduler empowers users to make smarter, greener, and more cost-effective decisions about when and where to run energy-intensive tasks. By automatically analyzing real-time and forecasted data for renewable potential, electricity prices, and carbon emissions, the tool enables both time-based and location-based optimization. This not only helps reduce operational costs, but also minimizes environmental impact, making it a practical solution for anyone looking to align their energy use with sustainability goals. That concludes the presentation. Thank you for your attention.